Good to go. Good afternoon, everyone. Thank you for your patience. Just sorting out, the inevitable technical difficulties that we have in this Zoom era. I want to welcome all of you to the 2024 Chhabra-Landau lecture. And I want to acknowledge a couple of our distinguished guests before I turn things over to Professor Stansel, who will introduce today's speaker. First, I want to sort of give you a little bit of a background about this lecture series. Ashton Chhabra was a student of Dr. Landau, the director of the Center for Simulational Physics, and he decided to endow this lecture series, which has been going on since 2020. We've had a number of distinguished faculty members coming here to tell us about their work, and today we're very pleased to have today's speaker. Just to sort of let you know, we're hoping that Dr. Chhabra is going to join us by Zoom. If he is not able to, this will be recorded for his later perusal. I also want to acknowledge the Dean of the Graduate School, Dr. Ron Walcott, and one of our Associate Deans of the Franklin College, Dr. Marcia Shepard, here. And of course, I want to acknowledge Dr. David Landau, director of the CSG, for his work in directing the center and putting together this series of lectures. So thank you, David, for that. And now I'd like to turn things over to Dr. Philip Stansel, who will give an introduction for today's speaker.
Thank you, Dr. Rieger. So as Dr. Rieger said, this is the 5th annual Chhabra-Landau lecture, and it was established by Dr. Chhabra here on the left for Dr. Landau. Those are really recent photos, I think. And so a little background also on Dr. Chhabra. He is president of the Euclidean Capital, currently, and he received his MS in physics from University of Georgia, working with David Landau, and then he went to Yale, where he received his PhD in applied physics, and then decided to make a phase transition to financial management. And currently, before that, he was head of quantitative research at J.P. Morgan, and also managing director and head of wealth management strategies at Merrill Lynch. And at one time was the chief investment officer and head of investment at Merrill Lynch. So now, as I said, he heads the Euclidean Capital, and Euclidean Capital manages the investments for the Simon Foundation. Maybe you may be aware of that foundation, which is dedicated to advancing research in basic sciences and mathematics. Dr. Chhabra has established this series of lectures to honor and celebrate David Landau's pioneering work on Monte Carlo simulations of condensed matter systems, and also the fact that David Landau is the founder of the Center for Simulational Physics. And here's just a few papers from Dr. Chhabra and Dr. Landau a number of years ago. So, let's see those. So I'm not sure if Dr. Chhabra is online.
No, not yet.
That's it, okay. So unfortunately, he had to be out of town and couldn't make it to this lecture. Anyway, so now I have the privilege of introducing today's lecturer. Okay. It is Dr. J. Michael Kosterlitz of Brown University. Dr. Kosterlitz received his master's and bachelor's at the University of Cambridge, and then went on to the University of Oxford, where he received his doctorate. He then had a number of fellowship positions at the, excuse my Italian, Istituto di Fisica Teorica, in Italy, and then at Cornell University, also Birmingham University, before he became on the faculty line at Birmingham, going from rank of lecturer, senior lecturer, to reader, which is equivalent to assistant associate professor here. But then he came across the pond and joined Brown University in 1982. So he's received a large number of awards throughout his career, and I'll just mention a couple of them, or we'll be here another 30 minutes. He received the Maxwell Medal in 1980. In 2000, the Onsager Prize. And in 2007, he was named a Fellow of the American Academy of Arts and Sciences. But in 2016, he received the Nobel Prize in Physics, which he shared with two other, oops, wrong screen, this one, eminent physicists. Okay. And his citation for that award was for theoretical discoveries of topological phase transitions and topological phases of matter. And later he also joined the National Academy of Sciences, amongst a number of other awards. So today his research has kind of made a transition, and he's studying out-of-equilibrium systems, what we're going to hear about. So before we welcome Dr. Kosterlitz, we have a little award to give him. So if Dr. Kosterlitz, David Landau, and Dr. Rieger can come up. Come right up. We have a little certificate. Come on up.
Gotta have the photo opportunity here.
Okay.
Where do you want me on the other side? Sure. Okay, over here.
There is a check that comes with this, but I do have. Okay, great.
I realize that's not quite as nice as the last one you got, but we hope you'll take it.
Now,
Oh, yes, yes, of course it is.
Right, thank you very much. Wow. All right, so stay up here. So without further ado, let's welcome Dr. Kosterlitz to UGA.
Okay, I'll need to hold that for you.
Now we can get your talk back up.
Yes. Okay, well, thank you very much for the invitation and the very flattering introduction. The title of this talk is...
Go ahead.
It's wavelength selection by additive stochastic noise in a driven out of equilibrium system. And it just started off out of curiosity because, you know, if you have a system approaching thermal and mechanical equilibrium, we all know that the selected stationary state is the Boltzmann distribution. So that's the unique stationary state. But that particular process is basically the driving force is derivative of a potential. But there are many evolution which are not describable with the driving force is not something as simple as the derivative of a potential, and so it's not obvious what the final state will be. So after all, if you have a potential, then it's pretty clear that the final state will simply be the, you know, the minimum of the potential free energy or something like that. And so in my old age, I decided to try to look at a simple toy model, and it resulted in a few papers. You know, my student was Saloni Saxena, and we got a couple of Phys Rev articles, and then then I found a group of Chinese collaborators, Yong Kong Chen and so on, and basically and Ping Ao, and we published a couple of papers and proceedings of the National Academy on this problem of selection. And so the papers are basically a partly analytic demonstration of a unique state, but the point is that the selection is done by the random stochastic noise. And this sounds a little bit counterintuitive. And so of course, it decided that we should look at a really simple system, trivial system. And the simple system is in one space dimensions, a so-called stabilized Kuramoto-Sierpinski equation, but with additive stochastic noise. Now, of course, the potential extensions of our theory are to, for instance, the problem of evolution of biological systems, of course, question mark. This stabilized Kuramoto-Sierpinski equation, even in one space dimension, has many interesting states, depending on the value of the control parameter, which you can call alpha. You see this alpha in the equation here. So the equation of motion is the first equation. And this f of h has got this linear term, which will control the modes which grow. These are fastest growing modes. Whenever the coefficient of the linear term is positive, then the mode will grow from zero. And of course, there is this nonlinear term, basically this square of the gradient squared of the field. And then there's some stochastic noise, which is represented by this eta, and the probability distribution of this eta is Gaussian. Okay, it's got strength, which I can call epsilon. Now, the important point is that the selected state is independent of the strength of the stochastic noise, and is determined entirely by this, if you like, this control parameter alpha. As long as alpha is less than a quarter, the mode will grow. And so what happens is the narrow band of modes will increase in size, their amplitude will increase in size, the nonlinear term will mix them up, and eventually it spits out a periodic state with a unique periodicity. And this unique periodicity is basically controlled by this parameter alpha, as long as alpha lies in some, it's not too small. Okay, you see, the point is that if you ignore everything except the linear system, you have this a band of growing modes. The horizontal axis is the wave number, q, and you see this is all the modes decayed back to zero, except for a narrow set of q values. And there is one particular q value, which is the linearly most unstable mode, at least the mode with the fastest growth rate. And naively, one would expect that at the end of the day, once everything is, once his growth is finished and settled down, one might expect that it's the fastest growing mode, which is at q squared equals basically a half, which is the selected wavelength. But that's not the case. Now, to start with, we decided to look at values of the control parameter alpha for which only the fundamental is unstable. So in other words, we keep this control parameter alpha less than a particular value, which as far as we can figure out is 0.16, because at this value, the second harmonic also becomes linear unstable. And then the first and second harmonics mix together, and God knows what happens. And so to start with, we restricted ourselves to the situation where there's only one mode excited. You want to take the discrete Fourier transform of the system, because we want to work in frequency space, or rather wave number space. That's easier. So if you don't mind this technical stuff, this is just a quick description of the discrete Fourier transform. Now, of course, the discrete Fourier transform is actually not quite as easy as one might think, because now we've got a finite system. So we've got a discrete set of possible values of the wave number. And we want to look at derivatives. So really, we're interested in what happens around a particular wave number. And so to calculate derivative, we really have to look at adjacent values of the wave number. And that gets a little bit complicated, but it's a way of getting around this. So the simulation algorithm we use is, we can write the field, the Fourier transform of the field, as u sub k at t plus 1, as a function of time, t plus 1, use a semi-implicit algorithm so that which is the equation sort of halfway down. You've probably all seen that before. Now, the beautiful thing about this semi-implicit algorithm is that the time step, this delta t, we can choose very large without, and the algorithm is stable. The point is that if you use just a simple forward step, if the time step is too big, you run into all sorts of horrible instabilities. Now, if you're trying to simulate the system to very long times, which you have to do to find a stationary state, then if you are stuck with small time steps, you have to simulate for a hell of a long time. But with this algorithm, if you're not too worried about accuracy, which we're not, we can actually use time steps up to about 0.3. So if you're trying to simulate for, let's say, a time evolution of, say, 10 to the 8 time steps, the point is that changing the delta t or the simulation time makes no change, and so we can assume that we reach a stationary state. Now, in the just as quick explanation of symbols, capital N is the number of grid points, and H is the separation of the grid points, and most of the simulations are done with the grid points spacing of a half, which is accurate enough. Most simulations are done with a simulation time. A system length of 2,000. In other words, good. But of course, this requires with the number of grid points we require with our lattice spacing of a half, n equals 4,000. The noise strength, which is labeled by this symbol epsilon, has to be unrealistically large, unfortunately, in order that the algorithm can explore all possible configurations. it's a bit like doing a Monte Carlo simulation in an equilibrium situation, and you want this Monte Carlo algorithm to be able to explore all possible states. So that the price one pays for solving this Langevin equation is that the noise strength has to be chosen unrealistically large, because if we don't do that, you get stuck in some minimum. You can see there's if you look at the noise spectrum, at least the power spectrum, that's the plot on the right, there's a big peak at a particular wave number. And you can see to the right a small second harmonic, and further right there's still an even smaller third harmonic, and so on and so forth. But we're interested in the effects of stochastic noise. And so we do a simulation of stochastic noise. Some added stochastic noise. And here's a typical field configuration we call the field U of x and t for the control parameter alpha is equal to 0.2. And the noise strength happens to be chosen at epsilon 0.004. And on the right, in the picture on the right, we see a typical configuration in Fourier space as a function of, the wave number k is basically is characterized by an integer small n, and of course the allowed wave numbers q sub n are equal to 2 pi n over L, where L is the system size, and typically L is 2000. On the right, we still see, in the presence of noise, we still see of the power spectrum, we still see a large peak at a particular wave number. And we can argue this is basically the state that's selected. And of course, there are all sorts of, of oscillations due to the noise. And if we look at, we can see on the right there's okay, where are we? Okay, there we are. See, there's a magnified piece of the noise spectrum. Now, you may have small values of Q. Now, the reason why I point this out is that these low Q values, these fluctuations at small q, and these are entirely due to the applied noise, are very, very important for the selection. Because without these, there is no wavelength selection. Because you see this big fat peak there at n is about what? It's about 250. That is basically the selected wave number. Now the next slide. Okay. Now here we've got this happens to be the structure function, and what you see on the left is what happens in the absence of noise. Now and on the right, this is a picture of the power spectrum in the presence of noise. Now, of course, the data there is very noisy, but nevertheless, if you look at this closely, you see that on the left, in the absence of noise, there's a dominant large, growth mode, which is it's a mode which is of a particular wave number with the largest amplitude. And if you look at the Q value, it's very different to the value in the presence of noise, because on the right there's a graph of what happens to these modes in the presence of noise. Now, of course, there are large fluctuations, etc., but the dominant Q values in the presence of noise are completely different to the value, the wavelength, or the Q value, the absolute noise. So then we wanted to try to understand what's going on. And there is an alternative way of setting up the problem, in an alternative but equivalent description of the dynamics. This is described on this slide. We see that the time rate of change of the field is got a linear term with the linear operator is just the control parameter alpha plus the second derivative of the field plus the fourth derivative. Now, of course, the alpha is positive, and the fourth derivative gives us a positive contribution. Therefore, those two terms are stabilizing, but the second derivative gives us has a negative eigenvalue, and therefore that's destabilizing. Somehow, the combination of the stabilizing and destabilizing terms will give us some selected wavelength. And so here, what I've written down here is simply an alternative description of the dynamics. And it turns out that this description, that's basically the third equation on the slide. This is a more convenient description for the analysis, because it turns out that actually, although there is no, in the original Langevin equation, there is no obvious potential involved. However, in this alternative description, there is a potential. And the equation of motion is in this equation halfway. Oh yeah, the first equation written down at the top of the slide. And of course, this operator D is a dissipative piece, and it's a standard Hermitian operator, but this thing we call Q is a transverse part, so that the matrix language, the transverse of Q is equal to minus Q, now it's anti-symmetric. Now, to find the potential phi, because if we can find a potential phi, which depends on the states, that means in order to find the selected state, all we have to do is minimize this potential. And so to find the potential is fairly simple. The quadratic part of the potential is simple. It's just, a half u dagger times its linear operator u. And the nonlinear part, we can write as, you can actually also write this down, at least for this problem. And you see it's that awful looking expression halfway down the slide. Of course, one of the problems is that we want to find these, in this language, matrices, D and Q has to be antisymmetric, and D has to be symmetric. And so in order to, if we construct this function G, which is described here, this certainly reproduces the equation of motion. But we have to find this antisymmetric Q matrix, and then what we have to do is we have to basically find the potential phi, which is not this phi sub 0, but it's something different, and it obeys this nasty-looking equation, which is third from the bottom. And basically, that's the problem we have to solve. Now, the point is that all these manipulations, we can show fairly simply that it does reproduce the original equation of motion. Oops. But that's not enough. Okay, so we want to look at what happens near a stationary state. And we can do this by the following set of manipulations. Okay, this is all very formal, but it can be done. And so basically what we find is that basically the equation of motion reduces to, just the simple the simple force, and the force can be represented as a derivative of the potential. And there's some more formal manipulations which show that this potential, or the potential difference, okay, and so the idea was, if we find one stationary state, we can extrapolate to a nearby stationary state. And so let's suppose we find a first stationary state, which we call A. Then we extrapolate to a nearby stationary state, which we call B of X. Then the change the potential going from A to B. The total change of the potential going from A to B is this rather complicated looking expression where these V's are basically eigenmodes of the matrix at the stationary state called A, and these stationary states flow towards the stationary state which I call B with an eigenvalue which we call lambda. And the potential difference between the states A and B should be this potential difference, which we call delta phi BA, which is given in that last equation. And given all these potential differences, we can get the global potential, which is what we're looking for, by summing over all possible paths from one stationary state to another to get a path-independent potential, which will depend only on the wave number. And what we want to do is to compare analytic potentials with numerical potentials. And the numerical potentials we obtain by simulating this, if you like, the stabilized Kuramoto-Sierpinski equation with noise. Then what we do is, for some time, then we turn the noise off, let the system relax to some periodic state for some time t sub s, and repeat this many times to get the potential, which we call a function of t, the relaxation time, t sub s, and the agreement with the analytic potential is that phi is not bad. So the left-hand graphs are basically the analytic graphs, and the right-hand graphs are the simulated probability distributions. And you see that what really is meaningful is the minimum of the potential. And we notice that the minimum of the potential seems to be pretty much independent of various things like the lattice spacing and and so on and so forth. If we assume the dissipation is very small, so that the transverse operator dominates, then, in fact, the dynamics decomposes into a set of independent two-dimensional subspaces, which is quite nice. And so, in other words, this this transverse matrix we can call Q decomposes into a direct sum of independent pair subspaces. And we can write the dynamics in the equation halfway down the page in terms of a symmetric matrix S and a transverse matrix T acting on the time derivative of the field, and this is equal to the gradient of the potential, plus, of course, the noise. And of course, the noise actually obeys almost a fluctuation dissipation theorem because its correlation is just proportional to epsilon, the original noise strength, times the symmetric part, and of course, delta t minus t prime. So basically what we do is we diagonalize. The numerical work consists of diagonalizing that n by n matrix, which is a big one, which equals D plus Q times the matrix R, to get all the eigenvalues and eigenvectors of the matrix. We can measure an overlap between the various subspaces found from the matrix with different elements, and a measure of the overlap is given by this fancy formula, which must lie between 0 and 1. Now, if the overlap is equal to 1, that means that the pair is completely isolated and the pair approximation is pretty good, and the analysis will actually mean something. So here's an example of the sort of thing that can happen. You see, suppose we have a stationary state, and that's the point at the center. And then we look at some perturbation where we start off some distance from the stationary state and let the system evolve. And we see that it sort of spirals in towards the stationary state. That means that the stationary state is stable. However, in the absence of noise, there is a situation where we can get where it doesn't actually spiral into any stable point, but it just goes round and round in a limit cycle. And one of the entertaining things is that if we look at the evolution of a particular two-dimensional subspace, for small values of the control parameter, we see that the limit cycle, which is indicated on the top right curve, a picture, appears for zero noise or zero dissipation. Right? So the beautiful thing about this other formulation is that we can simply change the strength of the dissipation at will. On the bottom left, we can see how the evolution is a function of time in terms of a deviation from the stationary state. You see, what happens is that we started off at some amplitude, and it oscillates between the two possibilities, and gradually the strength diminishes to zero as time evolves, and then it increases, decreases, and so on and so forth, so that actually the dynamics is actually much more complicated than one would expect. Basically summarize what I've said so far by a set of, I can't read my own writing, but sort of conclusions and questions. And we see that the study of this simple one-dimensional Kuramoto-Sivasynthi equation shows that the dynamics is much more complicated than expected. And adding this random stochastic noise it's very, very important, has some very important but unexpected effects. And the noise acts, now this is something that is surprising and completely counterintuitive. The noise actually acts to select out a unique state from a continuous band of possible states, at least in the limit of vanishing noise strength. This leads me at least to expect that we might be able to investigate selection of an evolving biological system where the stochastic noise, now one might imagine the stochastic noise is the bath of virus and bacteria which we all live in contact with. We can start speculating that it's not surprising that humans evolve to an approximately unique steady state. I mean, after all, we think about an adult human, and all adult humans are essentially the same pattern. Well, what are we? We're tubes about 2 meters high with 2 arms, 2 legs, and so on and so forth, and a head. Basically, we're all the same. We might differ in some minor respects, like, there's some male, some female, some black, some white, some brown, but those minor differences, those are really minor differences. The basic pattern is a tube about 2 meters high with four essential appendages. And this pattern is basically a stationary pattern. The adult human is basically it's a driven out of equilibrium system. We're certainly not in equilibrium. As if we were in equilibrium, we'd be dead. But we are all driven out of equilibrium systems. But for some reason, we evolved to essentially the same unique stationary pattern in the adult state. I mean, every species does this. If you look at an adult cow or bull, they're basically all the same, about the same size, etc., etc., etc. And so it's interesting to speculate that the adult adult members of any biological species have all evolved to a unique stationary pattern. At least that's the hypothesis that I'd like to put forward to you. And it's a rather intriguing thought that we should be able to find a theory. It seems that the bath of the noisy bath we're growing in, as I say, you can regard the bacteria and viruses, etc., as a source of stochastic noise that we can't get away from. To our way of thinking, after doing this simple model, it seems to us that this bath of stochastic noise is an absolutely essential ingredient in the evolution of any system driven out of equilibrium system, or, if you like, any species of animal. Now, this may be a very heretical idea, but I like to think in terms of these heretical ideas because it's fun. And one of the most important things about doing physics is to have, to pick a problem which nobody's solved and to have a lot of fun doing it. So, that's really the end of what I've got to say. I hope you learned something from the rather garbled exposition I gave you, but I hope you learned something and got intrigued at least. Thank you for your attention.
Okay, do you have any questions for Dr. Kosterlitz? Over there.
Okay. What exactly does the Kosterlitz-Sikocinski equation describe originally? Because I kind of missed that.
Well, the original equation, of course, was a deterministic problem. And I just got interested in, it contains a lot of the physical characteristics one sees in a lot of different systems. Things like, pattern of directional solidification, things like that. But it's also an incredibly simple model. It contains all the essentials. As I said, I said we're dealing with a toy model. And the Kuramoto-Sierpinski equation is one of the simplest toy models which has which displays some of the essential patterns one sees in all sorts of physical systems, but it's also very easy to compute. So that's the reason it was chosen, no other reason.
So would you then expect that picking another toy model would give the same results, so that the noise goes
okay, let's put it this way. I have no reason to think otherwise. This is a situation where really very little is known. Driven out of equilibrium systems it's basically, it's wide open. And to a first approximation, nobody knows anything about it. Some people claim they do, but I don't know. And since I basically made my career out of doing equilibrium stuff, I thought, in my advanced years, I don't care what anybody thinks. I'm going to do what turns me on for a change and have fun. And that's what this is all about. And that's my advice to all students and so on. Pick a topic and have fun doing it. So I have no particular motivation for picking this Kuramoto-Sierpinski equation. It's just that it's a very simple dynamical equation. At least it's one of the simplest equations I know of that's not trivial. And if you want something really trivial, you pick a linear equation, but that's boring. And it's clearly not going to describe anything real. Something like this could be an approximation to some real pattern-forming problem. And there's a lot of systems which are pattern-forming problems. I'm thinking about an evolving biological system as a pattern formation problem. And as I said, we're driven out of equilibrium systems. We're driven by food intake, etc. We're subject to all sorts of external perturbations, but we all evolve to roughly the same, indistinguishable, to a first approximation. And the question is why? Why does this happen? One of the interesting things is that in this toy mathematical game, it's the stochastic noise that does the selection for you, which is strange. Now, as I said, the only motivation for choosing this particular equation is for simplicity. You could construct something much more complicated and possibly even more realistic, but that would make life even harder than it already is.
Can I ask kind of a follow-up question?
Sure.
So, could this model tell us when, maybe why, bilaterals appeared? You know, before just a blob with no symmetry, and then bilaterals appeared on the Earth. You know, maybe there's some information on the time scale for that to occur.
So, I mean, basically, the results of our investigation say that basically it's the strength of the noise that determines the time scale. The stronger the noise, the shorter the time scale. And that makes some sort of sense because you might expect that a more noisy environment, a less hospitable environment, one's evolution would be even faster. You know, because the species wants to survive.
I'm wondering when you say select, I mean, it will convert some state. Anyway, right? How do you know? When you say select, what do you mean by select? There are many infinite numbers that can convert.
Right. I mean, in this model, there's basically a continuous band of possible states. For a given value of the control parameter, it's alpha, which I chose, there's a unique state picked out. You know, if in a deterministic system, without any noise, the state that you end up with will depend on the initial conditions. But with the presence of noise, it doesn't care about the initial conditions. And the state that's picked out is unique. You know, this is from a possible continuous band of periodicities.
I forgot your name.
James. Yeah, so I'm not super well versed on this, so excuse me if I'm a bit ignorant from asking this, but you're applying this to a biological system in which humans develop. And so we are able to use this and apply it to different systems on different scales. So we could potentially demonstrate something like a fractal nature in biological systems from the microscopic level to humans to larger scales.
Okay, I mean, in this sense, I think in the sense you're talking about, the noise is on the microscopic scale. And so, this affects what happens on a more macroscopic scale. So I am a bit surprised that it worked out. Now, because people were saying, look, you know, you normally think of that noise, you know, screws up nice patterns and so on. But here we've got a situation where the noise is an intrinsic part of the selection process to pick something out. And that sounds a little bit counterintuitive, to say the least. But the surprising thing is it seems to be correct. Given that, it's probably something worth following up. Now, it's a bit surprising to think about, you know, okay, you've got some growing species, and one of the essential things about its evolution is the bath of crud it's living in contact with. Well, okay, our claim is that this is the case. And one of the things that we're very gung-ho to try to do is to look at a real biological system and see if the ideas actually work. Okay, I mean, what we're doing is only in its infancy. As I said, it's a study of a toy model. mean, the Kuramoto-Sierpinski equation, you can say, okay, we've got a reservoir of possible patterns, but it's nonlinear and therefore essentially insoluble. But here we are, it works. Given values of the control parameter, which could be some, I don't know,
Maybe we could take some input from our biologist over here, Professor Arnold.
I was going to ask you, what if you took a different toy model, which is also worked on by Kuramoto, but it was for coupling an array of oscillators, and there's only one coupling parameter in the model, the coupling constant.
Mm-hmm.
And the question is, I mean, it's tractable because you can actually do something analytical if there's no noise. It is a system of ODEs, but what happens when you add the noise onto it? Do you think you would get different?
I have no idea what'll happen in your case.
Yeah.
And it's the effects of the noise are so surprising that.
But it could have a similar.
It could have.
Have a similar, but it would be nice. It would be a nice generalization. So you have this simple model by Kuramoto in the long game.
Sure.
And then you have another Kuramoto model, but it's slightly more complicated. It's not one equation.
Right. I mean, in my primitive opinion, this whole question of driven out of equilibrium systems, which are, let's say, ubiquitous, is wide open. Nobody understands much about it. And all sorts of, just in this, investigating this trivial model, all sorts of fascinating phenomena appear, which I tried to allude to but probably failed. But it really is a wide open field. When, to a first approximation, nothing is really known. Because basically nothing is soluble, as you can see. As soon as you put stochastic noise on, which in our opinion is essential. Very little is known and understood. I mean, the only place I think where things are understood is, for example, if you think about a system approaching equilibrium, then you can think of that as a dynamical system, but the driving force is a potential force. It's basically the derivative of, if you like, the free energy. But the stochastic noise, it's like, temperature fluctuations, that is essential because, you could regard this problem as sliding down the sticky hill and ending up in the deepest minimum. But if you think about this sticky hill, there's going to be there's nothing to prevent there being subsidiary minima. But we know the first thing you learn in statistical mechanics is the system ignores those and ends up in the deepest minimum. But it won't do that without the noise. So even in the simple-minded system, the stochastic noise is essential. Well, if you like, that's the thermal fluctuations. And so we just sort of put on the stochastic noise and asked, what does it do? And it seems to do all sorts of mysterious things.
Okay. All right, let's thank Dr. Kosterlitz. Before you leave, Dr. Rieger is going to tell us what's next on the program.
Thank you, Dr. Senzel. So I wanted to remind everyone that immediately following this, we have a reception upstairs in the Center for Simulational Physics, so the northwest side of the building. So you're free to attend that. Some light snacks will be available. And also I want to make sure that for any students who are either signed up for the colloquium course or who are in the quantum mechanics course, to please make sure to sign up to say that you were here so that we can record your participation in the event. Okay, thank you.